So this fifth sample problem is just kind of an interesting one, again, getting us to think about ionization energies and the fact that every atom wants to lose electrons to kind of get to be like a noble gas. Remember, it always takes energy to remove electrons, as we can see with these positive values for ionization energies in kilojoules per mole. But what this problem kind of gets us to think about is if we look at these ionization energies, again, they're kind of increasing steadily, right? As we remove electrons and become more and more positive, it becomes harder to keep removing electrons. So we kind of see this stepwise increase here. We're getting harder and harder, and then all of a sudden we see a large jump, right? And we see a large jump, and we have to think about what that means, right? So again, atoms want to lose electrons to be like a noble gas. But noble gases, being unreactive, are happy where they're at, so they don't want to lose additional electrons. So looking at this jump between the removal of electron 5 and then removal of electron 6, what we can infer here is that tells us that we have a species with 5 valence electrons. And you might need to watch this video again or pause it and think about it, because it's not going to be very long here. Because once we know that there's 5 electrons and we're in row 3 of the periodic table, it's going to be easy to see who we are. We'll go through that in a second. But just to highlight again, very easy or relatively easy comparatively to remove the first electron, second electron, third electron, fourth electron, fifth electron. But if we try to remove another electron, we're not happy. And that's because removing 5 electrons got us to a noble gas, but removing that 6th electron means removing an electron from a noble gas, and that's not good. All right, so if we look at row 3 of the periodic table, 1 electron, 2 valence electrons, 3 valence electrons, 4 valence electrons, 5 valence electrons. We must be phosphorus. So let's see again if we can walk through this logic. 1012 kilojoules per mole to get us to be isoelectronic with silicon. Remove another electron, isoelectronic with aluminum. Another electron, isoelectronic with magnesium. Another electron, isoelectronic with sodium. And remove one more electron and you are isoelectronic with neon. Happy, you're a noble gas. Try to remove one more electron and it's going to be hugely costly because you are disrupting something that's happy with a full octet of electrons.